Okay, 7.5 scalar and vector projections. So in this section, we're going to use the dot product in connection with projections, which has both a practical and theoretical point of view. So when two vectors, say we have vector A and vector B, and we'll call vector A OA. Okay, so I'll reference this diagram right here. So OA is going to be vector A. It's going to look like this. Okay, and then vector B is going to be OB, and it looks like this. Okay, say they're placed tail to tail. And then, of course, theta is the angle between them. Okay, so as a recap, we would have to use the parallelogram or the triangle in order to solve for the resultant, but that's not what we're doing here. What we're going to look at is the projection of A onto B. Okay, so as long as the angle between vector A and vector B is 180 degrees or less, the scalar projection of A onto B is ON, okay? This is going to look very different in quadrant, like say for example, we had quadrant 1 here, than it will if we were in quadrant 2, okay? Very different. So you have to think of this, okay? If we have OA and OB, then this right here is the projection of A onto B. That just looks like we completed the triangle, okay? And we use right triangle trig, okay? In other words, SOHCAHTOA and Pythagorean's theorem to apply geometric and algebraic vectors. So let's write SOHCAHTOA and then Pythag, okay? Pythagorean's theorem. Okay, so this one, you can't see it as much, but if we had an obtuse angle here and we had vector A and vector B, what ends up happening is we would extend vector B into into like the opposite direction, and this here, perpendicular, this would be the projection of A onto B. Okay, so scalar projection of A on B. So the scalar projection of vector A onto B is ON. Okay, so the actual scalar projection is this. It would be, I almost think of it like a shadow. It's ON. Okay, we would draw this line perpendicular from A, the tip of A, down onto B, or an extension of B, and that ON is the projection. Okay, and ON, if you think about it, it is the magnitude of vector A cos theta. Why is it this? Okay, so if we had theta here, I'll just do it for the acute triangle here. If we had theta here, we would have opposite, we would have adjacent, and we'd have hypotenuse. Okay, so what ends up happening is ON, which is adjacent. If you think about this, we would have cos theta equals ON, which is adjacent, over hypotenuse, which is vector A, or the magnitude of vector A, I should say. And that's just a cross multiplication. Okay, so that's vector ON. Just ON. Okay, so when I give you this, it's not necessary to memorize this if you understand where these numbers come from. Okay, lastly, and we're going to get into this a little bit more, the projection of A onto B, if we have A and B are perpendicular to each other in the first place, then it's 0. Okay, and as a reminder, cos of 90 equals 0. Okay, and we know that from the dot product. Okay, so let's talk about some of the observations about a scalar projection. Okay, so the projection of one vector onto another can be either scalar or a vector. The difference is the vector projection has a direction. Okay, and we're going to learn both of these equations. Okay, a scalar projection is obtained by drawing a line from the head of vector A perpendicular to OB or the extension of OB. If the point where the line meets the vector is labeled n, so yeah, that's what we labeled it here, then the scalar projection of A on B is ON. Okay? If the angle between the original vector A and vector B is acute, the scalar projection is positive, acute or 0. If the angle is obtuse, or 180, the scalar projection is negative, right? Think quadrant 1, which is the A quadrant. And this one, think quadrant 2, which is the S quadrant. So cos is negative. Okay, and then we know that if two vectors are perpendicular, okay, 90 degrees between them, the scalar projection is going to be 0, since cos 90 equals 0. Okay, the vector A on a 0 vector involves division by 0, which is meaningless, so this is not possible. So there's not going to be any projection from A onto like a 0 vector. Okay, and the scalar projection of A on B is not the same as B on A. It does not equal. So here's a box full of these equations, okay? The scalar projection of A on B is going to be A dot B divided by the magnitude of B. And it's going to equal the magnitude of vector A cos theta, where theta is the angle between A and B. Okay, and this angle again is tail to tail. Okay, this you're going to get a scalar. You're going to get a number. Now the vector projection of A on B, you're going to get a vector. It's going to be A dot B divided by the magnitude of B squared times vector B, okay, and it's going to equal A dot B over B dot B times B, like vector B. Okay, and then we're going to get into something called direction cosines, okay, and these are going to be for vector OP, which can be, remember like O is the origin, P is the point. So then obviously if we're going from the origin to the point and we subtract them, the point P, which is going to be ABC, is also going to be the direction or the vector OP, okay, still denoted by ABC. So then we're going to have three cosines. We're going to have cos alpha, cos beta, cos gamma. And we're going to put each of these components, A, B, and C, in the numerator, and then the magnitude of OP in the denominator. And those are called direction cosines. And alpha, beta, gamma are the direction angles between the position vector and the positive x-axis, the positive y-axis, and the positive z-axis. Okay, we're going to come back to that. We're going to focus on scalar projection first. Okay, so A, example 1, show algebraically that the scalar projection of A on B is identical to the scalar projection of A onto B. Okay, so what this means is that if we have A and B, this projection, which is 90 degrees, so the projection here is going to be the same as if we had A and double the length of B. Maybe that's 2B, okay? And the projection is still here, ON. Okay, so how do we show this? This is kind of a proof. So we're going to go vector A on B, vector B, and we're going to show that it's vector A on vector 2B. And we're going to show that these are equal. So I'm going to go ahead and write out the equation for vector A on vector B. Okay, it's vector A dot vector B over the magnitude of vector B. Now, A onto 2B is going to be very similar. It's going to be vector A dot vector 2b all over the magnitude of 2 vector b. Okay, so since 2 times the magnitude of vector b, like the magnitude of that, sorry, equals 2 times the magnitude of vector b. That's how you say that. Since these are the same, what we're going to do is, okay, we're going to rewrite the first equation, and then the second one, I'm actually going to it's pretty much like we're factoring out. I'm just going to rearrange this 2. So I'm going to pull out the 2. Remember, dot product and distributive property, any multiplication by a constant, it doesn't matter which order we go in. So I'm going to pull out this 2, and we still have like a dot b. Okay, over, I'm going to pull out this 2 in front of the magnitude, and we can just do magnitude of vector b, and those two 2's cancel out. So now we have vector A dot vector B over the magnitude of vector B equals the same thing. So that constant in the equation for the scalar projection ends up canceling out. Now B. Show algebraically that the scalar projection of A on B is not the same as A on negative 2B. Okay, so A on B does not equal A on negative 2B. Okay, negative 2 means that vector B is going in the opposite direction. So we want to make sure that we just want to show that this projection, ON, is not the same as this projection. Okay, when the B goes in the opposite direction. So let's go A dot B over magnitude of B. Okay, that's A on B. Okay, that's not going to equal A dot negative 2B over negative 2B, magnitude of negative 2B. So here's the thing. Since the magnitude of negative 2B is actually, because remember, as soon as we have negative in the magnitude, it's going to eventually be positive. Okay, so the magnitude of negative 2 vector B is actually 2 times vector B, the magnitude of vector B. Okay, and that's going to equal, so if I rearrange these, we were going to get negative 2 vector A dot vector B, and then that's going to be over 2 times vector B. And that does not equal A dot B over magnitude of vector B, because when we cancel out the 2's, this is still a negative in the numerator. Okay, you can, if you want, rewrite this as negative A dot B, even like this, over magnitude of vector B, and these are obviously not equal. Okay, so a recap. A on B is going to have the same projection as A on any constant times that vector B. Okay, any vector B in the same direction, just like a different length, a same projection. Now, A on B is not going to be the same as A on negative 2B. Okay, because that's a different direction. Okay, example 2. For the vectors, vector A and vector B, calculate each of the following scalar projections. Okay, so we're going to take, for A, it's A on B, and then for B, it's vector B on to vector A. Okay, so we're going to actually show that these two are not the same. So we're going to go vector A dot vector B, and this equals the magnitude of vector A times the magnitude of vector B times cos theta. Okay, so rearranged, if we took this B and we brought it down, okay, we would have A dot B over magnitude of vector B equals magnitude of A cos theta. Okay, so we're going to chunk this up. Let's do A dot B first. We'll do it in another color, okay? So A dot B, what we're going to do is for the dot product, because these both are in component form, we're going to take -3 and we're going to multiply it by -2. Then we're going to add 4 multiplied by 2. Then we're going to add 5√3 and multiply it by -1. Okay, so -3 times -2 is going to be 6, plus 4 times 2 is 8, plus 5√3 times -1 is just minus 5√3. Okay, 8 plus 6 is going to be 14 minus 5√3. Okay, if we actually do this as a decimal, we get 5.34. Okay, now we need the magnitude of B and then the magnitude of A as well. Okay, so let's do the magnitude of B. So what we're going to do is we're going to find the square root. It's like Pythagorean's theorem, but it's 3D. Okay, -2, 2, and -1. So we're going to have -2 squared plus 2 squared plus -1 squared. Okay, in other words, we're going to have the square root of 4 plus 4 plus 1, which is √9, which is 3. Okay, and then the last one, we're going to have the magnitude of vector A. So we don't need that for this one. We'll need it for the next one. So let's skip that for now. What we're going to do is we are going to find, we're going to put this all together, and we're going to do the magnitude of vector A cos theta. Okay, so going back up here, this is the equation that we're going to work with. A dot B over the magnitude of B. Okay, A dot B is this 5.34, and the magnitude of B is 3, so 1.78. So, in other words, the scalar projection of A on B is 1.78. Okay, so let's move on to question B. So B is going to be very similar to this. What we're going to do, instead of magnitude of vector A cos theta, we're going to have the magnitude of vector B cos theta. And instead of it being A dot B over magnitude of B, it's going to be A dot B or the magnitude of vector A. So we already have A dot B from the previous question is 5.34. Okay, and that's going to be divided by magnitude of vector A, which we don't have yet. So let's do the magnitude of vector A. It's going to be -3 squared plus 4 squared plus 5√3 squared. Okay, so -3 squared is 9, 4 squared is 16. So when we're doing 5√3 and this is all squared, I'm just taking this to the side of my paper. Another way of doing this is 5√3 times 5√3. Okay, 5 times 5 are normal numbers. I get 25. √3 times √3 is just 3. So this equals 75. Okay, so this is going to be root of 100, which is 10. So I can take this number and I can plug it back into this equation, which is the magnitude or the scalar projection of B onto A. And I get 5.34 divided by 10. So in total, I get 0.53. Okay, as you can see, this 0.53 is not the same as the 1.78. So we can even put, therefore, the scalar projection of B on A is 0.53. Okay, so this shows using real numbers that the scalar projection of A on B is not the same as the scalar projection of B onto A. Okay, so we're going to move on to direction cosines. So scalar projections are sometimes used to calculate the angle that a position vector, OP, makes with each one of the positive coordinate axes. So, example 3, determine the angle that the vector OP, 214, makes with each of the coordinate axes. So, if we remember these components, vector I is going to be 1, 0, 0, and then this is going to lay on the x-axis. Vector J is 0, 1, 0, and that lies on the y-axis. And vector K is 0, 0, 1, and that lies on the z-axis. Okay, so we're going to do this in 3 steps. First, let's find the angle that our vector OP makes with the x-axis. Okay, so we're going to go vector OP dot vector I is going to be equal to the magnitude of vector OP, the magnitude of vector I, cos, go alpha. Okay, so we did similar to this, and then we just divided this side by either OP or I, depending on what the projection was. This time what we're going to do is we're going to divide by both magnitude of OP and the magnitude of I, both sides, because what we want is we want this cos alpha alone. So essentially what we're going to get is we're going to get some equation for cos alpha in order to obviously solve for alpha of OP dot I, okay, over magnitude of OP, magnitude of I. Okay, so what I'm going to do is before I start to plug in, I'm going to do a little bit of the work at the top. Okay, let's find the magnitude of OP because we're going to need that for all of these. So this is going to be 2 squared plus 1 squared plus 4 squared, which is 4 plus 1 plus 16, which is going to be root 21. Now, we're going to find the magnitude of vector I. It's going to be 1 squared plus 0 squared plus 0 squared. So root of 1 is just 1. And the magnitude of vector I is also going to be equivalent to the magnitude of vector J and equivalent to the magnitude of vector K. Because essentially we're just interchanging the 1 for the zeros here. Okay, so we have root 21 and then we have 1. So going back to this equation here, we have vector OP dot vector I. So let's go ahead and sub in 2, 1, 4, and we're going to dot it by 1, 0, 0. And then we're going to divide it by root 21 times 1. So this is a little bit easy because if we have 2 and we multiply it by a 1, we get 2. 1 times 0 is obviously 0. 4 times 0 is 0. So these two we don't even have to consider. We only have to consider the x's multiplied by one another. So I get 2 over 21. Since this equals cos alpha, alpha is going to equal cos inverse of 2 over root 21, which, if we put this into our calculator, gives us 64 degrees. All right, let's now do, in another color, let's do the y-axis. Okay, so we're going to have cos, let's call it beta. Okay, and it's going to look like this. So I can write this out, OP dot vector j over the magnitude of OP, magnitude of vector j. Okay, so OP is going to be 214 again, and then vector j is going to be 0, 1, 0. And this is all over root 21 times 1. So these you don't have to consider because it's multiplied by 0. These you don't have to consider because they're multiplied by 0. So we only have to consider 1 times 1 in the numerator. So we're going to have cos beta equals 1 over root 21. Okay, to actually solve for beta, we're just going to inverse this side, and we get the angle of 77 degrees. Okay, so now let's do the z-axis. Okay, same thing. Let's go cos equals OP dot K over magnitude of OP times magnitude of vector K. Okay, same idea. So we're going to have 214, and we're going to dot it by 0, 0, 1. And it's all going to be over root 21 times 1. So when we're finding the dot product of this, the x and the y's don't matter. We are going to have 4 over root 21, because 4 times 1 equals 4. Okay, so we have cos gamma equals 4 over root 21. In order to get gamma by itself, we have to do the cos inverse of 4 over root 21, and we ended up getting 29 degrees. Okay, we can just round to the nearest degree. So let's think about this. What do these actually mean? So I'm going to write, therefore, vector OP makes an angle of 64 degrees with the x-axis, 77 degrees with the y-axis, and 29 degrees with the z-axis. Okay, that's the interpretation of those angles. All right, example 4. For the vector OP, determine the direction, cosine, and corresponding angle that this vector makes with the positive z-axis. Okay, here's the thing. So I'm going to provide the actual equation. So we're going to go vector OP dot, and we're going to go vector j, and that's going to be over the magnitude of OP times the magnitude of vector j. Here's the thing. So if we're doing, I'm going to do this on the side, if we're doing OP dot j, and we're doing -2 root 2, comma 4, comma -5, and we're doing the dot product with 0, 0, 1, here's the thing. Since this and this do not matter, we're simply going to get this z component of vector OP. So we no longer have to write all of this out. We can just simply, on the top, just write, you want to call this C or Z? Let's call it C. Okay, over, and I want to throw this out there. Let's talk about the magnitude of vector j. Okay, what is this always going to be? Well, 0 squared plus 0 squared plus 1 squared. Okay, it's always going to be 1. This is a unit vector. We know that unit vectors have magnitudes of 1, so we no longer need this either. So this is going to be simply C over vector OP. So our C value is -5. The magnitude of vector OP, we can actually solve for that. So that's going to be the square root of -2 root 2 squared plus 4 squared plus -5 squared. Okay, so that's -5 over. This is going to be, if you need to do this on the side of your paper, that's fine, -2 root 2. When we square it, it's going to be -2 root 2 times -2 root 2. So that's going to be 4 times 2, which is 8. Okay, so this is 8 plus 16 plus 25. The square root of that. So -5 over the square root of 49, which is just -5 over 7. Okay, if we talk about this being cos gamma, gamma is going to equal the cos inverse of this -5 over 7, which is 130, let's go 6 degrees. Okay, so we can simply say, therefore, OP makes an angle of 136 degrees with the z-axis. And now let's actually redefine our, well, let's just put it in this little box, our direction cosines. So we're going to have cos alpha is going to be A over the magnitude of OP. Cos beta is going to be B over the magnitude of OP. And cos gamma is going to be C over the magnitude of OP. Okay, these are the simplified forms. Okay, now we're going to talk about vector projections. So in the scalar projections, we saw that our answer was a scalar. Now, when we do vector projections, this is the calculation of a vector projection, A on B, is just the corresponding scalar projection, okay, of vector A on vector B, multiplied. So we still have to solve for the scalar projection. That's basically step 1. Then what we're going to do is we're going to multiply it by vector B over the magnitude of vector B. Okay, so this expression, vector B over the magnitude of vector B, is a unit vector pointing in the direction of vector B. So here's a little bit of a diagram. The scalar projection of A on B would be ON, but as a scalar. Notice that there's no angle there. There's no arrow. Now the vector projection of A on B is the same magnitude. This time it has an arrow because now it's a vector. Okay, and the vector projection of A on B is going to be the scalar projection of A on B times the unit vector in the direction of B, vector B. So this here is our equation for our scalar projection. Then this here is going to be our vector B over magnitude of vector B. So if we collect these two in the denominator, that gives us the magnitude of vector B squared. Okay, and the numerator is going to be A dot B times vector B on the side. Okay, it can also be rewritten as this magnitude of vector B squared can just be rewritten as vector B dot vector B. Okay, and vector B can't be a zero vector. So let's talk about this. Example 5. Find the vector projection of OA onto OB. So visually, if you're thinking OA, you might be thinking, okay, this is O and then this is A. And then this is OB. I always draw B a little bit longer. And then that's going to be 90 degrees. We're going to drop down from the head of A down onto B because it's A on B. And then this right here is going to be our vector projection and our direction. Okay, so this is 4, 3, and this is 4, -1. Okay, not drawn to scale, I'm just giving a visual. So let's do vector OA dot vector OB all over the magnitude of vector OB. Now, we're going to have 4, 3 dot 4, -1, and this is all going to be over the magnitude of 4 squared plus -1 squared. So in the numerator, 4 times 4 is 16, plus 3 times -1 is -3. Okay, in the denominator, we have 16 plus 1 under the square root sign. So we have 13 over root 17. Okay. So this right here is our scalar projection. Okay, so if you think about it, back up to this equation, we just solve for this right here. Now let's solve for this one. So we're going to have vector OB over the magnitude of vector OB. Okay, vector OB is going to be 4, -1, and it's going to be over the magnitude of vector OB. We already solved for this, it's root 17. Okay, so because this is still a vector, what I'm going to do is I'm going to rewrite this as 4 over root 17, comma, -1 over root 17. That's how that's going to look. So now we can do the vector projection of A onto B. And what that's going to look like is we're going to use this scalar, which is 13 over root 17, and we're going to multiply it by 4 over root 17, comma, -1 over root 17. And we're essentially going to distribute this in. So 13 times 4 is 52. Root of anything times itself is going to be just that number. So root 17 times root 17 is just 17. Now, 13 times -1 is -13. Root 17 times root 17 is 17. So this is the vector projection of A onto B. I'm going to give a better visual of this right now. Okay, so up here I just drew OB kind of on like the positive x-axis. Okay, I didn't rotate it, but we actually know these coordinates. So if this is our x-axis and this is 4, we have OA, which is 4, 3. Okay, so OA is going to look like this. Now we have OB, which is 4, -1. So I'm going to go -1s here. Okay, so if this is going to continuously go, which is OB, what ends up happening is we're going to go to the tip of A, and we're going to draw this perpendicular to B. Okay, so right here, this right here is our projected vector.